Right. So is my screen visible to you? Okay, I will just switch off my video for, yeah. So I would basically have a quick recap, and then we talk about temperature measurement of a surface. Just give me a moment. So I think we were talking about errors in temperature measurement. And we said that we're going to discuss error in temperature measurement at a surface inside a solid and a flowing fluid. We said that if when you are trying to measure temperature of a surface using a thermocouple, the thermocouple comprises of conducting wire. So some amount of heat is conducted into the wire from the point where you are trying to measure the temperature at. So essentially, the temperature that the tip of the thermocouple is at is lower than the surface temperature because of this heat loss. And we said that there are ways to sort of compensate for this heat loss, although rather in a more involved manner by applying heater. And we talked about bringing a thermal model, building a thermal model of the thermocouple. Typically, it has, if you take a cross-section of thermocouple wire, it has these two wires, one is positive and one is negative. And let's say, thermal conductivity of the wire 1 is K1 and the wire 2 is K2. Similarly, the radius are RW1 and RW2. And then typically these wires are encapsulated in a plastic. And let's say the dimensions of these is L1 and L2. So you can create this kind of geometry is very difficult to analyze using heat transfer because the geometry is irregular. So you can create a cylindrical equivalent of this model where you say that these two wires for heat transfer purposes can be considered into one single wire. And the outer covering can be, instead of using these flat sides L1 and then a rounded side L2, you just construct one circular cross-section R2. So basically this wire is having a radius of R1, and the annular region R2 minus R1 is basically the plastic, the polymer. So this is basically the R2 minus R1 region is more for insulation, and R1 is for heat conduction. So since the plastic has got very low thermal conductivity compared to the wire material, which is typically metal, this is the other cross section where this is basically R1 and this is R2. So the heat is basically conducted along the wire, and then eventually it goes to the ambient through the insulation layer, right? So heat flow is basically along the wire and then through the insulation layer in the radial direction, right? So then we said that if you want to build a thermal equivalent of these two different wires, you say that the thermal conductivity times area of the single wire is K1 AW1 plus K2 AW2. And if you say that the wires have same cross-sectional area, you can write that it is going to be K1 plus K2 into AW. And for the insulation layer, you again create an equivalent dimension. These are two. The outer radius is going to be L1 plus L2 divided by 4. So essentially, you have this kind of model built where you have conduction along the metal wire, and then conduction across the insulation layer, and finally convection into the ambient. Okay. So how do you create a circuit? You have the temperature of the wire, TW, somewhere here. And then this is the temperature of the insulator, which is the temperature here. So between the wire, edge of the wire and edge of the insulator, you have the insulation resistance, Ri. And then from the surface of the insulator to ambient, there is another resistance which is known as film resistance. This is the convection resistance. This is the conduction resistance. So we have from heat transfer the expressions for conduction resistance in a coaxial cylinder. See, this arrangement is like a coaxial cylinder having inner radius R1 and outer radius R2. And let's say the thermal conductivity of this insulation material is Ki. So the thermal resistance, this can be derived. If you know, for a coaxial cylinder, resistance is nothing but the temperature difference divided by the heat flux, right? Equivalent is like how you find electrical resistance is voltage difference divided by the current. So same way, you can actually find out the insulation resistance. I'm not going to show you the math here because that is part of heat transfer, but you can refer to some textbook on heat transfer. This is simpler to understand. And that if there is a coaxial cylinder having inner surface temperature TW and outer surface temperature TI, and the radius are R1 and R2, this is basically going to be the resistance. 1 over 2 pi Ki, Ki being the insulation layer thermal conductivity, into ln of R2 over R1. This is the conduction resistance, right, across the insulation layer. Then we talk about the film resistance. The film resistance comes because of a thin layer of fluid which remains stagnant closer to the outer boundary, right? And when you talk about convection heat transfer, you talk about a thermal boundary layer thickness. So this is a consequence of that, okay? And the expression for film resistance is basically 1 over, this is typically 1 over A into H. And here you talk about a unit length. So just you say that the perimeter 2 pi R2, unit length 1 into H, right? So this is 2 pi R2 into H. This is the film resistance. So now you can actually say that we take a specific scenario here before we apply this understanding there. So this is a situation. You have a fluid which is flowing at the top. So you have a fluid which is flowing here, and you want to sort of measure the temperature of this fluid using a thermocouple. Okay. So instead of directly exposing the thermocouple to the process fluid, you use a heat spreader. This is made out of copper, which is having very high thermal conductivity. The purpose of this spreader is to prevent direct exposure of this thermocouple tip to the wire, maybe to prevent to the fluid, to prevent erosion, corrosion, and also to capture heat from the fluid and supply it to the tip. Okay, so these are the two purposes of this heat spreader. So essentially, the thermocouple tip is mounted onto the bottom surface of this copper disc, and the copper, the other side of the copper, is exposed to the process fluid. So the heat basically goes from the process fluid into the spreader, then to the tip, then to the wires. So this is basically what happens in the thermal model. So you have the spreader, which is having a surface area of S, and the fluid is having a temperature of TF, which you want to measure. The heat transfer coefficient is HF. Okay. Now the heat from the fluid goes to the spreader, from the spreader goes to the tip, from the tip it gets conducted along the wire and gets conducted across the insulation layer and finally to the ambient. And let's say at the surface of the insulation layer and the ambient, the heat transfer coefficient is H. Okay. So now we need to analyze this scenario. So first, the heat.
Sir,
yeah.
can you just go back to that? Yeah.
Yes.
Why are we actually modeling using a fin analysis for the heat loss through the wire?
Sorry, can you say again?
We have take the last statement in the 3 points is that the heat loss through the wire is modeled using fin analysis.
Yes. So that is the one of the approach we can use to analyze this heat transfer scenario, because the fin is nothing but an extended surface. So this wire, the purpose of this wire is basically to conduct heat from the spreader and into the wire, right? Basically, there is heat loss. So what a fin does in a heat transfer application is to provide an extended surface for heat loss into ambient. So that is exactly the purpose that is happening here. So that is why if you want to analyze the heat transfer in this scenario, you have to take this wire as an extended surface or a fin. So we are analyzing this thermocouple as a fin, as I would be presenting subsequently.
So the thermocouple's end and the disc is actually welded together. Or soldered together.
Yeah, they are soldered together. So basically, the heat goes from the spreader into the thermocouple via the tip.
Okay. So now clear.
Okay. So I'll come to that. So basically, this will be taken as the base of the fin or extended surface or tip of the fin, and this will be an infinitely long fin. Okay, so we will talk about in a while. So the heat loss from wire to ambient is modeled using overall heat transfer coefficient. Okay. So what is overall heat transfer coefficient? Overall heat transfer coefficient takes care of both the conduction effect that happens from the core of this wire to the insulation layer and then convection from the wire surface to the ambient. So the overall heat transfer coefficient is obtained as 1 over H plus R2 over Ki ln R2 over R1 whole to the power minus 1. How it is obtained? So if you look at here, this thing that we just saw, so you say that you want to find out the overall heat transfer coefficient that is across the surface of this insulation layer. So we say that 1 over 2 pi R2 into the overall heat transfer coefficient will be equal to this resistance here, that conduction resistance, plus this, the convection resistance. Now from there, when you find overall heat transfer coefficient, so R2 will get multiplied here, R2 will get multiplied here, which will get cancelled. Now this is 1 over overall heat transfer coefficient. So when you want to find heat transfer coefficient, you have to have a negative minus sign. You have to find the reciprocal of the right hand side. So that is how this term is obtained. Okay, so this is the overall heat transfer coefficient considering both convection as well as conduction. So this is typical of heat transfer analysis, where total resistance is basically taken into account, because by doing this, you can just find out what is the heat flux. The perimeter of the wire is basically 2 pi into R1. R1 is the radius of the wire. And the product of thermal conductivity into area average is going to be pi R1 square into K1 plus K2. This is something we had already seen, right? Area of the wire, cross-sectional area of the wire into sum of the thermal conductivities of the wires. Product of thermal conductivity into area for both the wires. Now, as I was saying, that this heat loss from the surface into the wire, then from the wire to the ambient, can be analyzed by considering this thermocouple wire as a fin, as an extended surface. So, when you talk about fin, if you have studied heat transfer using fins, in fins, you talk about an effective fin parameter. So, M is basically the fin parameter, which can be expressed as square root of P H bar over Ka bar. P is the perimeter of the wire. H bar is the overall heat transfer coefficient, which has conduction and convection in it. And average of the product of thermal conductivity area is for the equivalent wire, which is coming from both these wires. And if I substitute for P from here and H from here, Ka from here, then I can simplify this as 2 into square root of H bar divided by R1 into K1 plus K2 square root. So this is the fin parameter. Okay. Now, assuming the lead wire or the thermocouple wire is infinitely long, the heat loss through the wire can be written from the fin theory in heat transfer analysis. Typically, the heat loss by an extended surface is typically expressed as this: M into Ka equivalent into temperature of the base of the fin minus the temperature of the ambient. So any heat transfer textbook on fin heat transfer will show you this formula. And typically M is represented as square root of P into H bar over Ka bar. So you have this formula coming from there. Now under steady state, this heat loss through the wire must equal to the heat gained from the fluid by the copper pad. See, this heat loss that is happening from the wire to the ambient we found considering this as a fin. Now this should be equal to how much heat is coming from the fluid to the surface, which is basically HA delta T, right? So HF into the surface area, which is S, HF into S, delta T. Delta T is temperature of the fluid minus temperature of this surface here. So we write that in this form, that the temperature, the heat that is coming from the fluid to the tip is basically HF into S into temperature of the fluid minus the temperature of the tip of the thermocouple. So now these two should be equal. And if you equate these two, you can find out an expression for Tt, that is temperature of the tip of the thermocouple. So Tt is in both sides, so you just do this simple math, take Tt in one side and then divide. Okay, so you have basically HF into S into TF plus M into Ka bar T ambient divided by HFS plus M into Ka bar. So here, the temperature of the tip is basically the convection heat transfer coefficient, HF, times the surface area of the spreader, heat spreader, temperature of the fluid, right? So these are fluidic parameter. Then plus, these are the fin parameter or the thermocouple parameter, M, the fin parameter, times Ka bar into T ambient, divided by HFS plus MK bar. Now you can see here that the temperature of the tip is like a weighted average of temperature of the fluid and ambient, and the weights being HFS, N2, and MK bar, right? So it says that the sensor temperature is weighted mean of the fluid and ambient temperature. Okay. Now your objective is to find out the fluid temperature. You are using the thermocouple as the sensor. So you are measuring TT. Now an ideal scenario will be when TT is just equal to TF. Okay. That means whatever temperature your thermocouple measures is exactly equal to the fluid temperature. And when that would happen? That would happen when this parameter M into Ka bar is 0, right? When this is 0, so this is 0, this is 0, and you have HFS, TF, and denominator you have HFS, so they will get cancelled. That means TT will just be equal to TF. In other words, you should have this M is basically square root of pH over Ka, right? So basically, you should ensure that square root of P into H into Ka bar will be equal to 0. Okay, should be equal to 0. So in that case, your thermometric error, which is the temperature of the tip minus temperature of the fluid. So from here you can find out, right? Temperature of the tip minus TF, and if you right side you do minus TF and you adjust the term, this is what you're going to get. So if you have the thermocouple geometry in such a way that the square root of these is very, very small, right? Then you can ensure that your thermometric error is going to be negligible. But in practical scenario, it is very difficult to design where the perimeter times heat transfer coefficient and thermal conductivity area is 0. It may be very small. So when you have a small M into Ka, which is non-zero, that will give rise to some finite thermometric error, okay, which can be maybe close to 1 degree or 2 degrees or something like that. But now you have a way of estimating how much is your thermometric error, because all these are basically design parameters and the ambient temperature and fluid temperature and so on. So you can actually estimate what is the error in your measurement. Right. So this is one kind of example that we see that this is, when it's trying to measure temperature of a surface, which is exposed to some kind of fluid. Next, let us talk about this temperature measurement error when we are trying to measure temperature of a point inside a solid. Okay, so there may be some application where you are trying to measure temperature of at a point which is located inside a solid. Okay, so here the thermocouple junction is placed inside a hole that is drilled in the solid. So basically this is the solid. Okay, here you have drilled a hole with a conical button, because when you drill typically you get this kind of feature. And now you basically insert the thermocouple here, because this is where you want to measure the temperature at. And this thermocouple wire, in order to fix this into the solid, you use some heat conducting cement in the annular space. Okay, so you have heat conducting cement filling up the annular space between the thermocouple insulation layer and the inner surface of this cavity. Okay, so if you take a cross section, okay, so this is what you're going to see. R1 is basically the radius of the wire, thermocouple wire, and R2 is basically the radius of the insulation layer. R3 is the internal radius of this cavity. Okay. So you have basically wire, insulation material, and heat conducting cement here, this annular region. So heat basically goes from this solid whose temperature you want to measure into the tip, and from the tip it gets conducted along the wire. Okay. So this is the scenario. Now we have to analyze this scenario. So how do we do that? So you basically create a thermal model of this. So you can see that this is the temperature of the solid. This is the temperature of the tip. Okay. And heat is basically conducted. You divide this into two regions. Region 2, which is buried inside the solid. Region 1, which is exposed to ambient. So whatever heat that comes from the tip to the interface, same amount of heat goes from the interface to the ambient, okay, in steady state. So this Q2 in the region 2 and region 1 have to be equal. This Ti is basically the temperature of the interface region. That means the point where the thermocouple is meeting the solid and the ambient, right at the surface level. Somewhere here is the temperature Ti. That is the interface temperature. So now, for heat transfer analysis, the first segment here, region 1, is similar to the previous example that we have taken. Okay. Like, in that case, we had the temperature of the tip, but here temperature of the interface. But this is a wire which is trying to, which is having a temperature, tip temperature of Ti, and then this fin is infinite. Okay. Exactly how we analyze the previous example. But the region 2, first of all, the fin is not infinite. This has this cavity has a length L. So this fin has a length L. This is a finite fin. Okay. Second, there is no convection here. Like here you have heat loss to the ambient, so there is convection heat transfer. Here only heat conduction takes place in the region 2. So we first analyze the region 2 of the thermocouple. And we just assume that the solid is at higher temperature than the ambient. So the junction temperature would be in between the solid temperature and the ambient temperature, which is natural. It says that if the temperature of the solid is higher than ambient, basically your interface temperature will be in between the Tt and T ambient, and Tt will be between Ts and Tn. Okay. So yeah, this we talked about. So the overall heat transfer coefficient in this case, here you have basically two concentric cylinders. Okay. So that means from here, heat can go here, and then from here, heat can go to R3. So basically, In this case, we have two different resistances, one resistance in the insulation, one resistance in the heat conducting cement. So if you want to find the equivalent resistance, you can find the equivalent heat transfer coefficient in the region 2 is basically like the previous case, R3 over the thermal conductivity of the cement, ln R3 over R2 plus R2 over the insulation layer, ln R2 over R1. Okay, so basically here, as I said, we are talking about the resistance of this section, R2 over R1, then R3 over R2. In R2 over R1, the property is K of the insulation layer. Here, R3 over R2, when you say, it is property of the cement. Okay, so that is why you are able to write this. So this is basically the overall heat transfer coefficient. Now, in the region 2, it is like an infinitely long fin. So you talk about the fin parameter M2 is PH2 bar over Ka bar, like the previous example. So the overall heat transfer coefficient for the exposed part of the thermocouple is given by so this is basically overall heat transfer coefficient in the buried region into the solid, and this is the fin parameter. Now, if you go to the region 1 here, that is exposed to the ambient. So here, this one is just similar to the previous case. Okay, 1 over H plus R2 over Ki ln R2 over R1 whole minus 1. And you can find the corresponding fin parameter for the region 1 to be P into H1 over Ka bar square root. Okay. So if you know the overall heat transfer coefficient and the fin parameter, first you can write that the heat transfer across the surface through the thermocouple should be the same. Therefore, you can write that whatever heat is coming from the wire to the insulator, the same amount of wire, same amount of heat should go from the wire surface to the ambient. So you write that Q2 is equal to Q1. Okay, whatever is going from the tip to the interface, same amount of is going from the interface to the ambient. Now, in the region 1, which is an infinitely long fin, which is exposed to the ambient, the heat loss is the same as that in the previous example. You have Mi Ka bar into the base temperature in this case is the interface temperature minus the ambient temperature. Okay. But if you go to a finite fin of length L, the expression for heat transfer can be found in a heat transfer textbook. The expression is different than what you would see for as compared to an infinite fin. So here, the formula is H, the overall heat transfer coefficient in the region 2. And this is exposed to the ambient. Sorry, it is exposed to the solid, right? We are talking about this region here. So overall heat transfer coefficient there into perimeter into length into the temperature of the solid minus the temperature of the interface into tan hyperbolic M2L over M2N. Okay, so this is the formula for temperature for heat loss through a fin of finite length L. Okay, so this again you can get from the transfer. And what you should note is basically this is the solid temperature, and this is the interface temperature. Okay, and all other parameters you already know. Now,
Professor, I have a
yeah.
question. Can I ask
Yeah.
if you allow?
Yeah, yeah.
Please. So, Professor, since we are like learning the formula for finite length fin and infinite length fin.
Yeah.
So, in the practical application, what is the interpretation of like fin length having infinite length in that sense?
Yeah.
What
So
I mean to say,
basically, in the
okay.
limit when L tends to infinity, okay, when L tends to infinity, this formula actually goes down to this. Okay, so this you can go through in a transfer book. And if you talk about a thermocouple wire, as compared to what you do if you want to measure temperature of a solid. So this is really, very large, right? And you want to know that mathematically when at what L this becomes an approximation, right? So typically, you say that for that, actually what happens is they non-dimensionalize this into some characteristic length scale, which could be, if let's say you take a cylindrical fin, it could be the diameter of the fin, right? So you non-dimensionalize with respect to the diameter, and typically, if the L by D ratio is greater than 10, it is taken as a long fin. Okay. So you have to non-dimensionalize this equation, and then you say that, okay, if my L by D ratio is greater than 10, I call this as a long fin. So, I mean, typically that is the case here, and you can approximate this formula when this condition is satisfied. Okay.
Thank you, sir. Thank you. I got it. So basically, it has the political, it has the meaning in physical world also. It's not
Yes,
like
yes,
just
yes.
a.
Yeah,
Okay.
no, it has meaning that as compared to the cross section, if the length of the fin is large, typically, much greater than the diameter, could be 10 or 20, then you call this as a long fin. Okay.
Thank you, sir. Thank you.
So now you equated these two, okay, and then you can find out the interface temperature Ti. So if you solve for interface temperature, you will find that the interface temperature is again a weighted mean of the solid temperature and the ambient temperature, and the weights W1, W2 being expressed as here. So W1 happens to be H2 bar PL into tan HML over ML, M12 over M12, and W2 is M1 into Ka average. So the thing is, once you know Ti, if you know Ti, that means the temperature here, you can use finite fin analysis. This is like equivalent to in heat transfer fin analysis, fin heat transfer analysis. This is like, the base temperature of a fin, and you are trying to predict the tip temperature of the fin, knowing all other parameters. So that formula is also available in heat transfer textbook. So if you know the base temperature Ti, you can find out the tip temperature T using this formula. So the temperature of the tip is basically the temperature of the ambient plus temperature ambient is basically Ts, because it is buried inside the solid, plus temperature of the interface minus the temperature of the solid, okay, temperature of the base minus temperature of the ambient divided by cos hyperbolic M2 into L. So you can know the temperature of the tip. So if you know the temperature of the tip, so you can see here, you wanted to measure temperature of the solid Ts. Now, what you are measuring is temperature of the tip. So this difference is basically the error. And this error is nothing but this term. And here you can see that if your cosine of hyperbolic m2L becomes infinity, then this term becomes 0 and Tt will simply be Ts. And for that to be infinity, your m2 into L has to be infinite. Okay. So this is the conclusion, that if you want to measure temperature inside a solid and you want to minimize the error in the temperature measurement, that means you have to ensure that the thermocouple tip temperature is same as the solid temperature. Then you have to design your system such that this M2, which is square root of pH2 over Ka bar, into L has to be very large. Right. So I would just talk about one more thing, and then I will have to share the other slide actually. Let me do that. So next example that we are going to take is that of a thermometer well. So typically this thermometer well we incorporate by creating a slot in a tube. So this is like a tube. Okay, this is the center line of the tube. Flow is happening inside the tube. You want to measure the temperature of the fluid, TF, but you don't want to, create a hole and directly expose the thermocouple to the process fluid, because maybe the process fluid is corrosive. So instead of measuring the temperature of the fluid, you want to measure the temperature of the surface. Now, if you just mount the temperature of a thermocouple right on the surface, it may not depict the temperature of the fluid, because the heat transfer area between the fluid and the surface is very limited. So one approach to solve this problem, and that will have a higher time constant. One approach to solve this problem is to create a thermometer well into the process fluid. So you basically create a hole and you insert a tube like this, and this is basically intruding into the bulk of the fluid and creating a significant amount of surface area. Okay, if you did not introduce this tube here, you would have gotten only this much area for heat exchange between the fluid and the thermocouple. Now, by doing this, the heat exchange surface has really enhanced. Now, you introduce the thermocouple like this, and you measure the temperature of the upper surface of this cavity here, somewhere here. And so heat basically flows from the process fluid into the tip and goes into the wire. Part of the heat also goes from the fluid into this tube wall, and from the tube wall, the heat can be lost into the ambient or this duct wall through radiation. So if you do not neglect radiation, particularly when the temperatures are very high, the radiation heat transfer you cannot neglect, because sigma, which is the Stefan-Boltzmann constant, is typically 10⁻⁸. So at reasonably low temperatures, your T to the power 4 becomes still negligible compared to 10 to the minus 8. So your convection heat transfer is normally neglected at low temperature. But in applications where temperatures are significant, you cannot neglect the radiation heat transfer that happens from this well surface and the ambient, in this case, the duct wall. So you have to consider the convection heat transfer, conduction heat transfer, and radiation heat transfer. 3 different kinds of heat transfers we have to consider here. So this is a typical thermocouple arrangement that we do when you are trying to measure temperature of the fluid. So this is basically the thermocouple tip. This is the thermocouple wire, and which runs like this to the data acquisition system. So you create a well sort of thing in the tube, and with some thread, and this basically goes, and you can tighten it here, and it just is held in place. So if let's say the process fluid is a gas, and let's say the gas temperature is higher than the ambient, the duct wall temperature, typically the heat flow will be from Tg to the thermocouple tip, and then it will go from the thermocouple tip to the ambient, and basically by conduction. But there can also be radiation heat exchange between this plug wall and the duct wall. So you basically, this is heat transfer wise, this is like a cylinder in cross flow. Okay, cylinder is sticking in this direction, the axis is in this direction, the flow is happening in the perpendicular direction. So heat transfer wise, this situation is similar to a cylinder in a cross flow scenario. So for that situation, you use the heat transfer coefficient is obtained from this Joukowski's correlation, which is something that you can study in convection heat transfer. So where the Nusselt number, which is representative of heat transfer, can be expressed in this form, some constant times Reynolds number to the power m and Prandtl number to the power n. So where these values of C and M and N depend on the Reynolds number and Prandtl number. So depending on the Reynolds number range, the value of C is going to be different, and the value of M also going to be different. Depending on the Prandtl number, you have the value of N. Okay, so this is known from convection heat transfer for the Nusselt number. And this is basically the convection part. You can also analyze the radiation heat transfer. Typically, the radiation heat transfer takes place between the temperature on the surface of this well, okay, and but the temperature will vary along the height direction here or x direction here. So temperature of that to the power 4 minus temperature of the wall to the power 4, right? So that is how we estimate, the radiation heat transfer, which is epsilon into emissivity times the Stephan-Boltzmann constant into T to the power 4 minus T wall to the power 4. Basically, temperature of the plug or the cavity minus the wall, the tube wall temperature to the power 4. So this is a fourth order term in temperature that you want to measure. So in most scenarios, you can linearize this equation. You can approximate the radiation heat transfer as 4 epsilon sigma into T wall to the power 4 into T minus T wall. So now you can see that the temperature is now a linear function. So this factor 4 epsilon sigma into T wall to the power cube is referred as some radiation heat transfer coefficient. Okay. So now with that, the various heat fluxes that are crossing the boundaries. What are the heat fluxes that are crossing the boundaries? So you can see that this is the temperature of the wall here, the tube wall. This is the temperature of the tip, right? So the heat basically conducts from this end of the cylinder to this end of the cylinder. So this is considered as a concentric cylinder. So you can see here, heat is coming by conduction and heat is leaving by radiation into this cross-section of this plug or the cavity material. So length is delta X. So Q conduction is basically H into A into delta T. So basically H into P into delta X will give you the cross-sectional area into Tg minus T. So first the temperature is coming from the gas into the surface, right? So this basically this heat transfer that it is talking about.
So P is perimeter over here, Nazar, right, Nazar? P?
Yeah, P is the perimeter. Yeah. So perimeter
Okay, so
into
2 pi r.
Yeah.
Okay, sir.
2 pi r L gives you the surface area of the cylindrical, right? Yeah.
Right. So delta X is the length, and hence
Yeah,
it is.
P is the perimeter. So this T gas minus T basically goes into the cylinder conduction. Then you have radiation. HR is the radiation heat transfer coefficient. Again, P into delta X. Now T minus T wall. That is the radiation heat exchange happens between this surface and the wall. In addition to this, you have heat conduction coming from TT to T wall, right? So on this surface here, sorry, X is positive in this direction. So here the heat, let's say this is at X, this is at X, and this is at X minus delta X. So heat conduction is basically Kw, the conductivity of this wall material, into area of cross section of this, because this is like an annular ring, into dT by dx. That is the temperature gradient here. That is the heat that is coming into this cross section. Now heat leaving is Kw into A dT by temperature gradient at X minus delta X. Here it is X. So X is in this direction. If this is X, this is delta X, this is X minus delta X, right? So now we have all the heat exchanges that are taking place. So we have from TT to TW by conduction, T gas to the surface by convection, and T on the wall to the tube wall by radiation. So we have all these heat exchanges. So if you can write the heat balance equation, energy balance equation, from there you can actually solve and find out how the temperature of the tip is varying and what is the corresponding error, which is temperature of the tip minus temperature of the gas, and how you can minimize. So I would stop here, but we can continue and talk about it in the next class. In the meantime, if you have any question, we can discuss.
Hi, sir. I have some questions.
Recording stopped.
So,
Yeah.
Thank you. So, like, the question is, what is the purpose of having that the well actually? Like, is it to get the stabilized reading from the measuring junction?
Yeah. So what happens is, see, if you just put a thermocouple right on the tube surface, then you see that the temperature, the thermal connection between the fluid and the tip is very weak, because it just like, for example, here you did not create this cavity, you just mounted it here. The thermal connection between the tip and the fluid is very weak because the heat exchange area between the tip and the fluid is very little. Okay. So by creating the well, you have basically now areas multiple times. Okay. So that is basically the reason why we want to create a well and not just mount it on the surface of the tube, basically to enhance the sensitivity of your measurement. Okay, so if there is a small change in the fluid temperature, you should be able to quickly really detect it. Okay.
Okay, sir. Okay. So just one more question. Like this is
Sorry, I lost your voice. Yeah. Can you say that again?
So, okay. In this case,
We're
Your
not
voice
actually
is not
audible.
audible.
Yeah, we're not audible.
Oh, is it better?
Yeah.
Yeah, sir. Okay, sir. So if we are having a like a square or rectangular duct, and if we are placing that the thermocouple on that, will we get a like a refined reading? Like maybe like this case, is it this is a cylinder wall. So maybe like then maybe like positioning the tip on that surface may be difficult, and maybe like we may not get the right result. But if we have the squared duct or a cylinder or a rectangular duct, and will it gives us a proper result, sir?
You said that this bottom of the surface.
Yes, correct.
So in
Correct.
this case, the
Yeah.
bottom of the this slot is basically circular intersection. So you can nicely mount it on the surface.
Okay, sir. Okay, I was mentioning, I was trying to without well, like for this case, the well is a cylindrical
Yeah.
type.
Yeah.
But if we are having without well, but the duct is of a squared section, cross section, or rectangular cross section, and if we are positioning this thermocouple on that surface, will it help to get the refined reading?
See, the thing is, basically why they do that, you have a lot of the tube wall has so much conduction that is happening along the length of the tube wall, right? But then whatever heat response that is coming from the fluid will get, conducted in this direction, and nothing much may reach into the tube. So basically now this way you are isolating the duct wall from the thermocouple getting a good response from the fluid. Okay.
Okay.
Because the tube wall itself will be very thick.
Yeah, agree. Yeah.
Whatever heat exchange is happening, quickly it will go in this direction. So the response will be not that strong as opposed to
Okay.
this.
Sure, sir.
Ramram,
Sure.
just
Understood.
to add to Sir's point, just one more point. Basically, this cylindrical like shapes are very easy to manufacture. Okay, suppose you have a surface where you have to drill like rectangular solution, you have to drill, maybe you have to make, sorry, not drill. That's a very difficult process. You have to use unconventional machining, and probably that will not be manufacturing friendly. Just to add one dimension to it, I'm just telling it.
Sure. Yeah, sure. Thank you, Roshan. Yeah, thank you, sir. Thank you.
Sir, one doubt, sir, maybe little off from the topic, sir, but if I'm allowed to, sir.
Yeah.
As sir, any conduction means during conduction, if resistance occurs, that converts into loss. So any other loss, mostly that electrical loss or flow loss, that converts into temperature, that raises the temperature. In case of this temperature conduction, when there is a resistance, so there would be some loss, and where that loss goes, sir?
I don't, I'm not sure whether I got your point. See, the error happens because of there is a heat loss that is happening. See, when you put a thermocouple onto a surface, what you measure is different than what in reality is, because there is heat that comes out through the wire, right? Metal wire. So that is what we are trying to capture here. Okay.
Sir, what I was trying to ask is like conduction, during conduction, there is a loss. So in conduction loss, because of that internal resistance of the conductor, there is a loss. So that resistance generally, when resistance is offered, so energy cannot be created, cannot be destroyed. So where that energy, converted energy goes, sir, like that I was trying to
Which
understand.
resistance you are talking about? I did not get.
Thermal conductivity, that thermal resistance.
So thermal resistance is because of the geometry of the material, right? Thermal resistance is typically based on the shape, right?
Yes,
What is the radius and what is the thermal conductivity? That is the thing. So loss depends on the resistance.
yes, sir.
Okay.
So that converted energy, like suppose we have a temperature and we have a conductor wire. So
Yeah.
we have T1 temperature at the starting of the tip, and we have T2 temperature at the end of the tip. So we have a delta T. So that some amount of energy is lost in conduction. If I'm right, sir. So that energy, in which form it is converted, that lost energy.
Okay, so that is basically, depleting the temperature of actual temperature of the surface.
Yes.
Your thermocouple is works on the principle of Seebeck effect, Peltier effect, right? Seebeck
Yes,
effect,
sir. Yes.
which is a combination of Peltier and now the local temperature is less, so your output should have been higher than what you actually read, because there is loss. So the heat
Yes.
from the surface goes to the ambient. So this is basically, irreversible loss that happens, and the consequence is that you are not reading the actual temperature. So.
Okay, sir. Thank you, sir. Understood. Sir.
So just a small request actually from my side.
Yeah.
In order to understand the concepts that is being taught by you, is it possible to share some recommended videos to learn about these sensors or any instruments that you're talking about?
See this, what we are covering today's class, this is well documented in the S.P. Venkatesan book. So please go through the book. And the concepts regarding the heat transfer analysis, I think you can pick any undergraduate heat transfer book. It will have fundamentals.
Sanjals and Boyle is okay, na, sir?
Sorry?
Sanjals and Boyle.
Yeah. I mean, that heat transfer book is very good, and you can go to the fin analysis section and you can.
Professor, sir, may I just like request something, if you allow, sir, please. Sir, the exam that we have wrote is the question paper are very balanced in that sense. On a similar pattern, sir, the topic that you are teaching us, if you can provide some practice question paper, which will really trigger our mind as to what I mean to say is there are a lot of good concepts in this, but unless we do some problem, it is getting dissolved. So
So
if
we are supposed to solve some questions, right?
Ji sir. So
In the
basically,
class.
if you can just provide us some, what I mean to say, question paper, sir. So
Okay.
what we'll do is our batch will try to solve that, and if there is some what I mean to say is difficult concept which is confusing, or maybe
Yeah.
we are not able to grasp it, then we can have a better I would say, sir, session
Yeah.
rather
So
than
yes, I mean I got your point. So I
Ji,
think
sir.
I mean after we finish temperature measurement, I will give you questions. which
Right.
you can work on,
Yes.
and you can come back to me, and if you have doubts, we can discuss over one session, one class.
That will
So
be great.
I plan to do that maybe chapter by chapter. Okay, let us do it that way.
Sir, thank you so much. Sir. Thank you so much.
Okay. Thank you all.
Thank you,
Thank you,
sir.
Thank you, sir. Thank you.
Thank you, sir. Thank you.
Thank you, sir.